everyone, today we're going to be talking about the scientific method, which is the method in which psychologists practice their discipline. Let's clarify something. Science is a method. You think of scientists, you think lab coats, test tubes, and whatnot. But really what science is a method. It's a method of asking and answering questions. Okay? And psychology is a science. But there are other sciences as well. I'm sure you know that physics is a science, biology is a science, chemistry is a science. All of these are sciences. But they all use the scientific method. So in other words, physicists and psychologists essentially use the scientific method to ask and answer questions. The difference between a physicist and a psychologist is what they study. So, for example, chemists, for example, they study matter. Psychologists study behavior and mental processes. So, the science, not what you study, but how you study it. So what exactly is science? As I said, it's a system of asking and answering questions. And it's based on what is called empiricism. The knowledge is gained through direct observation. So scientists are looking at real-world phenomena. They are not making stuff up, essentially. They are looking at real-world phenomena, and they're basing their theories, they're making their conclusions based on what they see in the real world. They make tests using real-world observation. So that is what all scientists do, no matter what the science is. So all scientists use this method. We describe, we explain, and predict the events that we observe all around us. So we're describing it. Essentially, the description means that you are just observing what is around you and clearly describing what it is you see. You're not making any explanations as to why this is occurring. You're just flat out describing, this is what I see. So taking measurements. If you're measuring the weight of an object, you're describing something. That's an example of description. If you are explaining something, that's where you're starting to bring in theory. Now you're starting to say, well, why is this phenomenon happening? Okay? Again, so for example, you may say, why is this child having a temper tantrum? Okay? Now the description is, the child is rolling around on the floor screaming. Okay, that's a description of what is going on. The explanation is asking, why is this child having a temper tantrum? Okay? And, scientists are also trying to predict that. So maybe you'd be interested in predicting when the child would be more likely to have a temper tantrum. What circumstances would be likely to cause it? So, again, scientific method involves describing, explaining, and predicting. And again, a child having a temper tantrum on the floor at Walmart is clearly a real-world observation. So you're using empiricism, you are making an observation in the real world, and you are describing, explaining, and possibly predicting what you are seeing. And with psychology, we are describing, explaining, and predicting behavior and mental processes. Okay, so let's talk about the reasoning and logic that scientists are following when they're using the scientific method. If I heard the term inductive and deductive reasoning, well, this is relevant in logic and philosophy. It's also relevant in science, and it's relevant in psychology. Okay? And basically, Scientists do this all the time. As we gain more knowledge about the world, we're using both inductive and deductive reasoning to help us understand the world around us. Inductive reasoning to start out is you're starting with specific examples, specific observations, and from these specific observations you make general conclusions. Okay? It's driven by data. So the observations are the data. The observations are what you see around you. And you would call it probably a bottom-up process. The bottom being all the different observations around the world, and you're trying to build up to the top of that pyramid. What is the basis for all of that? So it's going from specific observations to general conclusions. This is relevant when it comes to scientific research, because with scientific research you may have specific research results, from one research result, one observation, one research result, another one, and you take these results and you say, how are they connected? How are these particular results connected in some way? Is there some way to explain all of these different findings? And you use this to build a theory. So you make all these observations, and from these observations say, I think we have a potential theory that might explain what we see. Okay? And that's inductive reasoning, and realizing you're starting with the specific observations. On the other hand, deductive reasoning, you're starting from the top. You're starting from the general idea, the general beliefs that you have. And so you're using these general principles, and now you're trying to apply these principles to try to do it to a specific situation. It's driven by logic. So now you're not starting with specific observations. You're starting with an idea. You're starting with a theory. And from this idea, from this theory, you now want to point to a specific observation that would support it. So your general theories help us generate specific hypotheses. So kind of looking at this picture here, summarizing it, inductive reasoning is from the specific to the general, from deductive reasoning from general to the specific. Again, the general explanations essentially can apply to many different things. But you're taking specific observations, and from those you are drawing the general conclusion. Now, so an example of this could be this. Let's say I have a general belief that all children are beautiful. Okay? So let's say I just grab my daughter Molly, my daughter Mandy, and I say, well, if all children are beautiful, let's put this to the test. And I look at Molly, and I look at Mandy, and I say, you know what? Molly and Mandy indeed are beautiful. And therefore, that result supports my general belief, doesn't it? All children are beautiful. My daughter Molly, my daughter Mandy are beautiful. And therefore, all children are beautiful. It supports my belief. Well, that was an example of deductive reasoning. You're starting with a general principle being all children are beautiful. You haven't looked at any children yet. You're making that general belief. I think all children are beautiful. Then you take your specific example, Molly and Mandy, and then I look at those children and I evaluate, well, it looks like they are beautiful. So therefore then I will conclude, I guess all children are beautiful. And that's deductive reasoning. Now, of course, you might notice a flaw with that. Just like there is a flaw with any kind of, potential flaws with any theory. Clearly, all children are not beautiful. As long as you find one child that isn't beautiful, it would sort of disprove the theory. But basically, yeah, you're starting with a premise that is is clearly not true. I mean, some people may believe all children are beautiful, but I don't think that you can make the claim that all children are indeed beautiful. So you're starting with a faulty premise. Likewise, if you're starting with a faulty theory, you might find one specific observation that supports the theory, but then find another observation that doesn't support the theory. So then you have some mixed results, and you may need to kind of go back and look at that theory. So that's deductive reasoning. You're starting with the general principle. Even if your general principle is flawed, you're applying it to specific cases, and then drawing your conclusions. Now let's look at it the other way, inductive reasoning. With inductive reasoning, you are starting with a bunch of specific observations, and then from those observations, you would then draw your conclusions. So let's say I go to a playground, and I look at the children playing in the playground, and I look at this child over here, and I say, yep, that child's beautiful. I go to look at the other child and say, yep, that child's beautiful. Look at another one and say, yep, that child's beautiful. Yep, that child's beautiful. And what if, lo and behold, every single child in that playground happens to be beautiful? Well, guess what? I'm going to conclude, well, I guess if all these specific observations of children in this playground indicate that these children are beautiful, well, then I guess I can make a general conclusion that all children are beautiful. And that is inductive reasoning. You're starting with specific observations. From these specific observations, you are then building a general principle to kind of explain it all. Well, is there a flaw here? Of course there is. You've just got one little playground, and you're making these observations here of these children, maybe 10 children in this one playground. And are you going to make the conclusion from these 10 children that all children in the world are beautiful? It's probably a pretty big conceptual leap to do that. But that also happens with science as well. You know, when you are running an experiment, it's only one experiment. When you are taking a sample from a population, it's only one sample. Even if it's 100 or 200 or 300 people in your sample, it doesn't include everybody in the population. So, as a result, when you are taking this particular point of view, when you are only taking a sample and you're trying to generalize to the population, there is always a possibility that there could be a flaw in this, that that your sample might not truly reflect what is really true in the population. And again, that is one of the major issues, one of the major dilemmas and challenges that scientists have to follow. But we'll talk more about that a little bit later.